Yeah, in the last class, we were able to look at the introduction to a microeconomics. Yeah, you're welcome. Please put off your mic. Yeah, if I you can turn off your mic. So in the last class, we were able to discuss the concept of individual uh, decision making. This class is a tutorial class. We want to revisit everything we discussed in the last class and also complete the entire lecture. So the topic is individual decision making. In individual decision making, we said we are considering how individuals make decisions using economic tools. So I said one of those tools an economist use in making decisions are models. Our models are those uh, expressions. It could be mathematical, it could be in any form. They are just expressions that we use to represent realities. Okay, so model depicts reality. So model enable us to make good decision in economics. So, like I discussed in the last class, I said for us to be able to construct a good model in making an individual decision, one needs to be able to make preference of his items or of his wants, what he wants to make decision on. He will be able to make a good preference. And that's why we are considering the first topic here as preference. So we are looking at preference relation, how these items or these uh, substances we want to make decision with, how are they related? So preference enables us to understand this concept. So when we look at preference, we say preference is just similar to set of items or set of alternatives. Okay. So preference are just what sets of alternatives that we are trying to make decisions with. I hope you remember that in the last class. Can I get a response?
Yes, we do.
All right. So I will say preference of items are denoted by set X. This capital letter X. That is what we use to represent sets, the preference of items. They are just collections of alternatives or all our wants. So, like this is a set of an individual who wants to go to law school. Another of his alternatives is to go to graduate school and study economics. Another of his alternative is to go to business school. Yeah, this person has three alternative in a set, and this is a set of preference. So it can be denoted by capital letter X or can be denoted by any symbol. Okay. Here is a set for a family who want to have a weekend being fun and they decide to go to opera, decide to go to rock concerts, other decide to go to what? To ice skating shows. So this is a set or is a preference for a certain family. Here is another individual preference, which is a preference of fruits. Maybe his preference is for apple, another person's preference is for orange, another person's preference is for banana. So the collection of this item is what set is a preference. Mathematically, we say is a set. I hope we don't have any problem with preference in this class. If you still do not understand preference, can you drop an emoji? You can also use the chat box, or you can mute your mic and speak up. Do we still have issues with preference? So I assume that preference is clear to everyone. Please use the mic. Let's make this class interactive, okay? Use the mic. Feel free. Discuss it. So we look at preference relation. We say preference relation uh, enable individuals to make decision, and we denote preference relation with a certain symbol. So this is the symbol which looks like greater than and equal to. Okay. So like I said in the last class, it's different from greater than. It's not greater than, all right, but it looks like greater than and equal to. So it is used to denote preference relation. Okay. And it's a binary operation. It's a binary relation. What we mean by binary relation? We are saying it can only accommodate two items at a time. This preference relation cannot be used for three items sequentially. No, it can only be used for two items at the same time. That's why it's a binary relation of a set of alternatives. If your set of alternatives contain 10 items, you can only relate two at a particular time when applying this symbol. Okay, that is what you are saying. And also, we use them in comparison. Let's say if we have a set X, capital X, which has some item, let's figure out two items in it. Let's say X and Y. So this symbol that looks like E is denoted by elements. This is called elements. So, or it belong. So X and Y are element of this preference set. Or we say X and Y belongs to this preference X and Y. That's what you are saying. So like you can rightly say here, the symbol is used to relate two items together, X and Y. So that is why it's a preference relation, it's a binary operator. Now, X could be anything, X, Y could be anything. X could be like what we have in the example earlier. This example, X can be going to law school, Y could be going to a graduate school and study economics. We want to look at their relationship. That is how we relate them together. Any question at this junction? Do you have any question? All right. In absence of no question, we proceed. So we said there are two derivations we can derive from a preference relation. When relating x to y, some some assumptions or some derivations that we can make out of it is that when we have x preferred to y, is a strict relation. So we denote it with this symbol. So x is preferred to y. What does this mean? It means no sitting on the fence. It's X is preferred to Y. They are. So when you choose X, you've chosen it. It's preferred to Y. No going back. That is what strict relation is saying. Okay. So you're not moving back. You are focused on X. X is strictly greater than Y. It's just like if you have a house that says we close our gates by 7 a.m. or 7 p.m. It means 7:01 when you come, you are late. That is a strict rule, okay? So that is what this symbol is saying. X is strictly preferred to Y. Yeah, so you must take note of that. But not Y preferred to X. The reverse cannot hold. But We can also interpret X preferred to Y as X is weakly preferred to Y. You can see this symbol. X is at least as good as Y. That's what it's also saying. All right. So, like we have said in the last class, whenever we have this relation between X and Y, we can read it as X is preferred, X is at least as good as Y, or X is weakly preferred to Y. So, but the reverse does not hold. Y does not you cannot prefer Y to X whenever you are using a strict relation. Okay, so and in the case of indifference, we can also derive indifference from this relationship. Okay, the indifference relation is saying the symbol is denoted by this that looks like theta or looks like tit, but it is not. It is indifference relation. So if X is indifference from Y, what does that mean? We have challenges in picking Y, in distinguishing Y from X or X from Y. They are virtually the same. So that is why, just like when someone gave us an orange of color yellow, we have two oranges that have color yellow. We won't be able to differentiate between them. When you pick one, it's like you're picking the other one. So that is what indifference is saying. X and Y, we cannot differentiate between them. So they are indifference, okay? So, and it also means that Y is at least as good as X, or X is at least as good as Y. So this relation. So when we are using indifference, we're also saying that Y is at least as good as X, or X is at least as good as Y. That is what I say. So let me get questions at this time. This is a tutorial class, okay? Can I get questions? Yeah, Emmanuel, can we get questions from you? Yeah, fine. Can we get questions from you? Yeah, ask us questions. Ask us questions. I'm waiting. This class is supposed to be interactive, okay? So ask your questions. Or should I ask questions? I have good questions to ask. Should I? Can we proceed? Let me assume you understand it to this point.
Yes, please, you can proceed, sir.
Right.
Please continue, please. We are getting what you are teaching.
All right. Thank you. I'm excited. I'm excited with that. All right. So now, when we are dealing with preference relation, okay, so is it all relation that we assume that are correct? So when relating two things together, are we assuming that all the time, or in every 100, in every 10 that we pick, are we saying that they are correct? No. Okay, that is the answer. No is the answer. So not all preference that we can make decisions with. So not all relation we can make decision with. So we have to filter out those relations that are rational. Okay, so that's why we have a rational a rational preference. So when do we say a preference is rational? Remember, a preference relation Instead of saying a preference relation, mathematically, we represent it with this symbol. Okay, this symbol means preference relation. Preference is the set itself. This is preference. This is preference relation. I hope this is clear. All right. So whenever we take preference, are we saying all preference are rational? No. Okay. So there are rational preferences and there are irrational preferences. So we can classify our preference into two, rational or irrational. So when we say a preference is rational, it means it satisfies two axioms. The first axiom is completeness, and the second axiom is what? Transitivity. So our preference must be transitive and our preference must be complete before we can say a preference is rational. For every complete preference, it means we are taking the relation between two items from a particular set. Okay, that set must contain two items for us to check completeness, or from a particular set, we're only picking two items for us to say this set is complete. All right. So I prefer in a set X or in a preference set of X, I'm picking X and Y. So and I say X is at least as good as Y, or Y is at least as good as X. Please pay notes to this attention. Pay attention to this or here. That means both of them are not holding at the same time. X is preferred to Y. In other cases, I can say Y is preferred to X, or both. What both means, you are saying indifference. Okay. And I say both, X is indifference from Y. I'm unable to pick X from Y. That's what I mean by both. All right. So X is preferred to Y, or X is at least as good as Y for me to have a complete set. So for transitivity, all I'm saying, I'm picking three elements from this set. Okay, that set must contain at least three items for me to say I want to check transitivity. X is at least as good as Y is at least as good as Z, and the implication is that X is at least as good as Z. That's what we are saying. So transitivity. Like the last class, I laid more emphasis on this. X is at least as good as Y is at least as good as Z, X is at least as good as Z. So that's the implication. What does this mean in reality? Let me recap. Okay, it means that if you have three items, okay, if I say I'm picking apple for breakfast, uh, orange for lunch, and banana for dinner. So when I prefer apple to orange, yeah, it's good. That's my breakfast. I prefer orange to banana for lunch. All right. So for my dinner, it also means that I prefer apple to what? To banana. So that is what it means. So transitivity. So any preference that does not satisfy these two axioms, it means that it's an irrational preference. And in an irrational preference, we don't have a lot of theory to back them up. So no time to waste on checking irrational preference. It's irrational, is irrational. We didn't know that when something is rational, we can make a whole lot of decision with it. Something that is correct, we can make decisions with it. Something that is not correct, no need to waste time on it. That's why economics does not give a lot of preference to irrational preference. Okay. So now there are some prepositions here. Okay. So we studied this preposition last time. We say if we have a preference relation, we can derive three things out of it. Okay. We can say the preference is a strict preference. It could be what? Indifference. And we can have also this relation. All right. So if we are having a strict relation, then some assumptions that we can also infer include e irreflective. So it means that every item we pick, they are irreflective. That means they are never, we can never have a situation where an item is reflecting itself in a set. Remember from the definition of set can only contain one item at a time, one alternative. Okay, so a set cannot contain the same item. You can't have a set that contains the same item in multiple times. Okay, so from that assumption, we can say that anytime we're having a strict preference, definitely no item reflects itself in that set. X cannot be preferred to X. Okay, means X cannot be preferred to X. All right, so and also we can have an assumption that is what? Transitive. And also, if we are having an indifference, we can have this relation. So there are proofs to this. Can anyone give us a proof for this? Or do you have a proof? How to prove these three assumptions? Do you have the ideas on how to prove these three assumptions? Anybody? Anybody with ideas on how to prove these assumptions? The way? All right, let's prove it because the objective of this class is to learn some proofs. Okay, we have to learn the proofs, the mathematical proofs of how some of these occur. So I will share my screen and show you some of the proofs on how to. We'll try and prove at least. If you can't prove the three, you can prove at least two out of it. Then I'll give you the third one as an assignment. All right. So to show me the proof of the third one in our next class. Is that okay? So let me prove the first two. All right. Is my screen visible? Can I get a
Yes,
response?
it is visible.
All right.
Go
Thank you.
ahead.
All right. So here is the proof. So preposition says if if we have if we have this preference that is rational, then this is what? Reflective. Is irreflective. That means it does not uh, prefer to itself. And it's also transitive. Okay. So we are going to look at this, how to prove this. So the first step is to use the assumption of what? Completeness.
Hello?
Yeah, can you hear me?
Yeah. Please, is this one part of the recording?
Yes, it's part of the recording. Oh,
Is that
yeah,
is
yeah,
that
it's part. I think you can see the screen.
okay?
Yeah, it's part
All
of the
right, thank you.
recording. Yeah.
All right, thank you.
Please, I will encourage you to write down all of this in your note. Have a note for this class, okay? Because we are going to solve a lot of mathematics. Have a note, write them down. Very
Y-
looking at the screen will not make you to understand the course properly. Write them down at your convenience. Okay. That's how you learn this micro. Write them down, solve them. All right. So now we are going to use those assumptions. Remember the assumption of transitivity, the assumption of completeness. We are going to use them to prove This number one. So what does this mean? By completeness axiom, x is preferred to x. So remember the completeness axiom, it says x is preferred to itself. So x is at least as good as x. That is what this is saying. X is at least as good as x for all x we pick in our preference. So anything, any x I pick or any item I pick for my preference set is the same thing as itself. So that is why it's complete. So once we have this, therefore there is a contradiction that says it is greater than itself. Okay, so that is why irreflexive does not hold. So what does that mean? It means that there is no what? Hence, there is no x in x such that x is preferred to itself. All right. So therefore, 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 we can say what? We can say that what? Our preference is what? Our preference is irreflective. So therefore, we can conclude that our preference is what? Is irreflexive. So we can conclude that our preference is what? Irreflexive. That is what that assumption means. So we have proved this irreflexive. So just two steps, it's not difficult. So let me recap again. From the law of setup, from the completeness axiom, which says anytime I pick an item from a set, it is the same thing as itself. It's at least as good as that item. Any item I'm picking is at least as good as that item. So it's a contradiction to say that that item is not preferred to itself. So it's a contradiction. So therefore, we can say it's what? Irreflexive. So we can conclude that is what is irreflexive. Now, suppose suppose that we have the next step is to show that suppose that x is what is prefer to what x. Okay. Suppose x is preferred to y or is preferred to y. What does that mean? Suppose we say x is preferred to y and y is preferred to z. All right. What does that mean? So it means that x, so this
X
x
is
is to
prefer
y
to
and y is preferred to z. All right. So what are we expecting from here now? What are we expecting? We're expecting that what transitivity should hold. X must be what preferred to z, right? So that is our expectation.
yes,
So
yes.
yeah, then so if we have that, then the third law can come in. So we can rearrange these three expressions to form a single expression because of the rules of mathematics, okay? If A is equals to B and B is equals to C, I can put them as a simple equation. So X is preferred to Y and Y is somehow is at least as good as Z, okay? So I can rewrite this three. Definitely transitivity as a core. So now I have proved transitivity with that. So this is the transitivity part. So that means this relation is specific, right? So this relation is what? Is transitive. Then I can as well. So that is the proof of completeness of this strict preference.
Oh,
Can I ask a question?
Yeah, go on.
Okay, so suppose that X is S is as good as Y,
Yes.
and Y is as good as Z. It
Yeah.
actually means that X is also as good as Z, and
Yes.
Z is equally as good as Y.
Is
But
weekly. Yeah.
weekly,
Yeah. Okay. You can also use equally as good as one. Yeah.
okay. So where I have the problem is in the conclusion
Okay.
that then X is as good as Y,
Yeah. X
and
is no X is preferred to Y.
okay,
This
good.
X is preferred to Y.
So this that conclusion you explained it with a statement. I can't get it. I didn't get it.
Okay. 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 But I think are you getting it now? Or I should explain it.
No, this conclusion, because if X is preferred to Y,
Y. Yeah. Y is at
and
least as good as Z.
so Y is as good as Z.
Yeah.
But from the preliminary,
This step.
is yeah. So
Okay.
it's showing us that S is preferred to Y
Yes.
and Y is preferred to Z,
Yes.
which actually means that X is preferred to Z,
Yes.
right?
Yeah. From this, even
Okay,
from this
that's the
conclusion.
logic. That's the
Yeah.
logic. But
Yes.
if X is preferred to Y and Y is preferred to Z, how then is Z equally as good as, sorry, how then is Y equally as good as Z since it is preferred?
Yeah. So since it is preferred, so because of this relation here, X is preferred to Y. Okay.
Yes.
X is preferred to Y. Y is preferred to Z. So logically, we can say there is relation. X has similarity. X has a lot of similarities with Z. Okay. So
Okay.
X
Okay.
does not strictly dominate X. So X does not strictly prefer to Z because of Y, which is preferring, which it dominates. So it dominates Y and it's also dominating, Y is also dominating Z. Definitely, uh, Y, Z is at least as good as Z. If you remember the definition of completeness, okay, this is what completeness is saying. I can pick X at least as good as itself anytime I'm even having a strict relation. So by the axiom of completeness, that is what we are applying to this guy. So that's why this guy changes from being this symbol to this symbol here. Don't know if that is clear.
Okay.
Okay, let me take it
I
again.
will know. I
Complete.
will know. I will know more about it because I am still thinking
So,
that if Y
so
is if Y is preferred to Z,
Yes.
then there shouldn't be any similarity with them.
By definition of completeness, if
Okay.
X is preferred to X, here X is preferred to Y. Is that not true?
Yeah.
So definitely, I can, when I'm having strict here, I can replace it with this guy. So this guy can just be okay. You know what? I will
Okay.
just so to make it more
Equally
clearer.
as good. Okay.
To make it more clearer.
invariably, what you are saying is X does not have a direct relationship with Z, right?
Yes,
It is the Y that relates to both X and Z.
that is it.
Okay, okay,
So now,
okay.
before we make this
I
conclusion,
understand now.
yeah, before we make this conclusion, we can say recall. Okay, we can say recall that Okay, you can say recall that. So let me quickly put this line in between. So you can see, like I say, recall that whenever x is preferred to x, recall that whenever x is preferred to x, we are using that assumption. So we can recall that whenever x is preferred to x, then we can conclude this way. So I agree that y, x strictly dominates y here. That is what I'm having here. Then I can make y or x have the same, be at least as good as y to be at least as good as x here. So that is the logic, and that is what we have in this. Look at this third assumption here from the assumption. So actually the first assumption leads to the third assumption. They are interrelated, okay? It's a thing that looks circular. So you can see that then if this rule holds, then you can see that x is strictly greater than z. So when we get to the third proof, and that is an assignment, so you have to show that x will be strictly greater than z whenever this occur. So from proof one that we've shown that we can record that that's from the definition of completeness that x, if x is strict to itself or to anything, definitely we can have this relation to hold. So that is how to prove transitivity. Then transitivity has occur. Yeah, that's the meaning. Because x is greater than y is preferred to z, and x at least as good as z, or x strictly dominates z from this. So we can also look at this first and this last. X strictly dominates z. So transitivity has occurred. So we can say that our strict preference is also transitive. All right. So let's go to the second proof of irreflexive. Of reflexive rather. So we say that okay, now we are making proof of this indifference. Okay, say that if our preference relation is rational, definitely this symbol or this indifference is reflexive. All right. So since we can look at this derivation, it's very important. Okay. So since we can assume that every element in a set is at least as good as itself, okay? Any item I pick, if I have a mobile phone, that mobile phone is as good as itself. No phone is better than the phone. I will assume that no phone is better than that phone I'm holding. So that phone is good. So X is at least as good as itself. So that is what this guy is saying. So since we have this in mind, definitely so is the phone. If I have this phone in two places, X is indifferent from itself. I cannot differentiate a Techno Camel 20i from itself. So it's still the same thing. So if I have them in two places, so is whenever X is indifferent from X, for X in our preferences. So that's what it's saying. So if X is indifferent from itself, definitely we can also say that X is at least as good as X. That is what this. So these two statements are the same thing. Okay, X is at least as good as itself. X is indifferent from X. We are saying the same thing. So whenever this occur, then we can say that what X is what reflexive. Okay, so we can say X is what reflexive. So so that's how we conclude that X is what? X is reflexive because it's reflecting to itself. Or like this case of strict, if I'm having this here, X is not greater than itself, so it's irreflexive. But in this case here, X is the same thing as itself, is reflexive. Okay, so and then if X is reflexive, then we can make some assumption now. Let's make some assumption. So the assumption is saying that what? Suppose that X is indifferent from X and Y is in. So anytime you see suppose, is an assumption, okay? So suppose that X is indifferent from Y and Y is indifferent from Z. What does that mean? Can anybody say that? What are we trying to, what should be the outcome here? Or what should be our expectation here? Anytime we have X is indifferent from X, Y is indifferent from Z. What is our expectation? Anybody?
Then X is indifferent from Z.
That's beautiful. So then X is indifferent from Z. So, but we can, then that's our expectation, okay? But we can also from the first line, we can return to the first line now and replace this, since we say this indifference, X is indifference from X, is the same thing as this. Then I can replace this symbol by a preference relation. So I can say that X is at least as good as Y is at least as good as Z, then Z is also at least as good as Y. We can reverse it because they are indifferent. So this, from this expression, X is at least as good as X. So that assumption. If we have X at least as good as Y, another commodity, okay, and we're having Y is at least as good as Z, another commodity, definitely I can return back to the left hand side of this expression, X at least as good as X, and I replace this by Y, I replace this by Z. Okay, so and I have this expression. So X at least as good as Y, Y is at least as good as Z. Definitely, since they are indifferent, I cannot differentiate between X and Y. I can reverse it, and that is the definition of what's it called?
Of
It's one
reflexive.
of reflexive. Thank you. So we can,
Okay, now, so it means you can reverse or even Y is as good as X also, right?
yes, you can also reverse this. Y is at least
All
as
right.
good as X. So
All right. Thank you.
yeah. So that is the definition. So from that definition now, so we can reverse it. That is indifference. Okay. It's only indifference that gave us that privilege to reverse it. In strict preference, you cannot do that reversal. So then I can conclude that. So I can say by transitivity, X X is at least as good as X, and what? X is at least as good as. Sorry, this should be X. Yeah, yeah. So by transitivity, I can say this, that X should be at least as good as Z, and I reverse it. Yeah. Okay. Sorry, pardon me. So here should be X.
Look at it clearly again. Look at it.
Yeah. Yeah, yeah, it should be it like this. By transitivity, yeah, I should have it like this. X is at least as good as Z, and Z is at least as good
Good as Y as X.
as X. So we can reverse it. Since I've reversed this one here, so I can reverse this other one. So the transitivity part. So the transitivity as what? As occur. So transitivity as occur. Then I can conclude. I can conclude that X is indifferent from Z, right? Because I was able to
Yes.
reverse it here. And also,
Yes. Yes.
thank you very much. And also, I can say that what my symbol, this my symbol, preference relation is transitive, and I have proved this side completely. Okay, and I proved that side completely. So it's meant to show that it is symmetric, and it's meant to show that what it is symmetry. So now, since transitivity, we've proved transitivity. We've proved irreflexive, that this indifference is irreflexive. This indifference is what? Transitive, and it's remained to show that what? It is symmetry. And when symmetry, what we mean by symmetry? It means X is transitive to X is indifferent from Y, then y is indifferent from x. So that is what we mean by transitive, okay? Yeah, that's what we mean by symmetry. Okay, when you can mirror something, you mirror it. The way you look it from the back is like you're looking at it from the other side. When you mirror it, that's what we mean by symmetry. Transitive, in symmetry, two things are also involved, okay? X and y alone. Since we know that y is what is strictly preferred to what x, right? So since we know that y is strictly preferred to x, is strictly preferred to z, all right, then we can say what? Then because of that indifference that we have, then we can also say that what? Z is strictly, oh, sorry, we are using x. If y is strictly preferred to x, then we can also say that x is strictly preferred to y. So we can do this reversal, okay? We can as well make this reversal to occur. All right. And once we make that reversal to occur, then we can, so since x is preferred to, is as least as good as y, then x is at least as good as then. Then because of the indifference that we have earlier, then x, we can conclude that what? X is preferred to, X is indifference. We can conclude that X is indifference from what? X is indifference from Y. So that's the first part of the symmetry. Then we can also make the reversal. So if from this other part here, we can also say that, so since X is indifferent from Y, similarly, we can as well say y is indifferent. So we can just make this reversal here. So we'll make this reversal here. So we observe that y is indifferent from x. This indifference is what? Symmetry. So that is the end of the proof for those two. All right. So I think we are all following. Any question at this point? Any question? So we've seen the two proofs. So the third proof is left as an exercise. Okay. So I just put it there. So the third proof is left as what? Exercise. All right, so the third proof there is left as exercise. So you can prove it at your convenience, and so it's an exercise. Don't forget. All right. So any question at this point before we proceed? I'm expecting questions. All right. In absence of no question, let me bring down my screen and continue with the other lecture. So those are the proofs of those three. So I will I would love to see the uh, proof of the third one in the next class. Okay. So we discussed utility function last time. I would say utility means what? Means the satisfaction we derive when consuming a particular alternative. So in preferences, we apply utility function to preferences whenever we have a rational preference. That means for us to have a rational preference, you know what that means? It must be complete and it must be what? Transitive. So that is what we have. So, and that is how we arrive at this preference. All right. So we say mathematically it's just a numeric assignment of numbers to preference. So if X is our set of preference, and when we are relating it to this set of a real number, we are just numerically what? Assigning them, okay? Assigning numbers to those preference in the set. How this is clear? Any question?
Can you repeat that again? The utility function.
All
And
right. Utility itself means numeric. Utility itself means the satisfaction one derive when consuming a particular commodity. That is what utility means. All right. So, and in applying this utility function to preference, what we mean is that we are applying a certain function. We are assigning numerical values, just your normal numbers. You are applying it to those elements inside a set. A set we know contains a list of items, right? Maybe you want to go to graduate school, you want to go and study law. Yeah, you want to go to law school or to business school, or you want to eat apple, banana, or orange. Those are the elements that contain in X. All right. So whenever you are assigning numeric numbers to them, what we are saying is that you are doing utility. Whenever you assign this to R means a set of real number. Real number means numbers from one from positive infinity to negative infinity. Any number you can find there, 1, 2, 3, 4, 5, see where you can count to, or negative numbers from -1, 2 to a point you can count to. So those are real numbers, okay? So whenever we are assigning these numbers to our utility, our preference set, okay? That means we've assigned a function, is a function. So we denote it by small u. You can see this expression is read. Let me read this expression for us. This expression is read that u, which is the utility function, is defined. This semicolon means is defined on a preference set that maps a real number. Let me come again. A utility function that defines on a preference set that maps real number. When this map means that is assigned to a real number. Okay. In a layman form, we can say that all those elements in that set are assigned. We assign number to them. That's what we are saying. So when we do that, so or we are comparing them with a set of real number. When you do that, is what utility. So we've applied utility function. Okay. So now, for us to be able to apply utility function to any preference set, that set must be rational. So, like I said here, I said only rational preference can be represented by utility function. Okay, but we can not only preference set now, we can do the converse. A set that is finite can also be represented by any word, by can be represented by utility function. What I mean by a finite set X, what I meant is that a finite set X is a set that is countable. So when I can count the element in that set, it's a finite set. If I cannot count it, it's an infinite set. I'll just put in the front of finite, infinite. So meaning that I cannot count that set. Okay, so that is fine. So for me to apply utility function, that set must be what? Must be countable, must be rational. Okay. So, what does this mean? So, if we want to define a preference relation, like we know that preference relation is a binary operator, a binary relation that relates only two items, x and y. Okay, so it relates these two items together. So you just need to apply your utility function to x, apply utility function to y, then you have this. What does this mean? It means the derivation that I'm going to have on set x or on x item or commodity x exceed this inequality means exceed the satisfaction I'm getting, exceed or equal to the satisfaction that y will give to me. That's how we define it in a lemma form, okay? But what this means is that the utility of alternative x is at least as good as y, okay? So I hope that explanation is clear.
Yeah, it is clear.
All right, thank you very much. So now we have second preposition. I have proved this preposition. You know, this proposition one I have here. I didn't prove it earlier, but I went somewhere and proved it. Okay, but proposition two, I prove it. So you must get used to my language proposition. Okay, so they are just uh, they are just like some. They are not theories though, but they are just expression that has been established, that has been proved. Okay, so it's an assumption that has been proved over time, and it is very useful. So we call them proposition. So now theory is the one that has been established. So before we see theory, we'll get to the middle of our course. Okay, we'll see me theory, but proposition, get used to proposition. So proposition says a preference relation this can be what can be represented by its function only if it is rational. So it's just like I'm repeating this definition here, okay, or this sentence here. So now let's see the proof. So the proof is also based on what? On those assumptions that we looked at. What are those assumptions? Completeness and what? Transitivity. We said before we can apply utility function, it must be rational, right? So now we know that it is rational. What are those properties of rationality? Completeness and transitivity. So our proof uh, to prove these utility functions, or to prove that every preference represents a utility function is rational, I will go and use the properties of a rational function or of rationality of preference to make my proof. Now, to use those properties, first, to use completeness. So we can show that this preference relation satisfy what? Completeness. So for me to show that this preference relation satisfy completeness, so because this function, what does this mean? Just it means that I am having a utility function that is defined on a set dot. This dot means that there are items in that utility function. So that is mapped to real function. So real valued function. Real value function means this is the real value function I'm talking about, R. So the real value function. So on X. So that what I have here is what I'm repeating here. Okay. So because this U is defined on a real value function defined on X. So this expression here represents what I have here. Like I said, U is defined on X that map a real number or real value function. So that is what I have here. So because this U is defined on a real value function, then any then any it must what? It must be complete for any value I pick here. So that is it. Why must it be complete? Because mathematician has already proved that real value function are complete. Okay, a real number system is complete. So mathematician has proved that. So based on that assumption, I'm free to say that this function is complete. So any preference relation that is defined on this utility is also complete. So that is the reason why we have the statement, because the real number system is complete. Definitely, any function that is defined on it, which is this preference relation, is also complete. So then I can have this from the law, from the completeness axiom. It means that whenever I have a preference relation that exceeds x that exceeds y. Also, I also have I can also have this, but not both. If it is indifference, I will have and here. I told us earlier to pay attention to that all the other time. So I will have and here, but in this case, it is all because it is at least as good as y. So it's completeness. Yeah. So it implies that what x is at least as good as y, or y is at least as good as x. Hence, I can say that what this operator is complete. So that is the first part of the proof. Now, to show the other part, remember a rational function has two properties, completeness and what? And transitivity. So I will also prove the transitivity by picking any three elements from my set X. Therefore, I will have X is at least as good as Y, and Y is at least as good as Z, or then, because this function, which is defined on the real number, represents this, represent the rational preference, then I will have utility of this to exceed the utility of x to exceed the utility of y. Yeah, and or utility of y exceed the utility of z. Definitely, utility of x exceed the utility of z. So that is complete. That's transitivity. So when this occur, so we can say x exceed what? X is at least as good as z. So, and that would be, so this implies that x is at least as good as what? Z. So thus we have showed that if that x exceeds y, y exceeds z, and z exceeds x is at least as good as z. So transitivity has been established. Okay, so that is the proof. Please master the proof. It's very important. All right, so these are the bases we are going to use to solve some other problem. So now, in the last part of this course, in the next 5 minutes, we talk about choice. So remember, I said anytime we are trying to build a model to make decision, the first thing we need to do is to pick a preference of our alternative. What do we want to make decision with? Okay, so we look at our set, we pick a preference. Okay, I want to make decision with an Android phone rather than an iPhone. So I'm working with an Android phone, so I'll pick my preference. So, but what's the choice of picking that preference? Okay, so that's how choice comes in. All right, the choice of picking that preference. So we said in the second approach to the theory of decision making, behavior itself is taken to be primitive object of the theory. So it's very important choice. So we must know the choice, the behavior, okay, of the choice of that definition of that All right, is set B. This is a coily B. All right, take note of that. And we have the choice rule. Choice rule, I mean the rules that are associated with that choice we want to make. There are rules that govern every choice we make. All right. So now the coily B is just a family set. What I mean by family set is that B contains a lot of B. All right. That means there are other B, just like we have a B contains is an element of B, or B is in this quality B. So just the way we have X and Y inside X, all right, so is B in B, all right. So we'll have some B's that we can derive in B. There are so many B's there. So B is standing for a budget set, okay? Don't be confused between this B and this B. Just like we have small x and small y inside x, so also B, they are also sets that are found inside this B. So that's why we said B is a family set, all right, of non-empty sets. So it means that it's a subset of X. What do we mean by subset? This B is gotten from this X. All right. So is we can this B is found inside this X. So that means every family set, every set we are picking comes from our preference set. So once we've made our preference, so we have other choice, we have other set that we want to make our assumptions with. So that is the first thing that is what this B means. Also, we look at choice, the choice rule. So we said choice will correspond to what? It's just the rule that enables us to assign a non-empty set. All right. So this dot means they are budgets, or there are other sets. They represent sets from a particular set. So every budget set B, for all this B, it contains from this family set. All right. So a choice rule. Okay, I'm trying to explain the choice rule consists of what? A set. I'm interpreting this first two, I'm interpreting them here, right? So meaning that a set of choice sets, which is a subset of X. So that is what we mean by the first one, this family set. There are a lot of other sets that is contained in S. All right. And the choice rule is just a map, just like the way we have our utility, which is a map. All right. The choice rule is also a map. All right. So it's a map that map all alternatives to X. So the interpretation of CB is the set of alternatives in decision making. A decision making might choose from B. So that's what we mean by what CB. So anytime you see C dots, all right, know that that dot represents we are expecting a certain
Real
element.
number.
Yes, thank you. Certain sets inside this place. So and so that's what it means. So I can, instead of me writing dot here, I can put B. You know that is a set or a real number that is coming there because we are assigning it to a set, a preference set. So also I can write it in this form most time, okay? So don't be confused. Anytime I write it in this form or I'm writing it in this form, don't be confused. All right. So now let's look at some examples before we end the class. I think in the next 3 minutes I will end the class. Thank you for your patience. So suppose that X is a set. Let's get this example clearly. All right. Suppose X, this X is a preference set and is what? It contains X, Y, and Z. All right. These are the elements of X. X can be orange, Y can be uh, apple, and Z is banana. Okay, so and my coily B is a family set. All right, you can see that this B contains what we have in X. No, every set is a subset of its own self, right? So this set contains this set X contains 8 sets. If you remember in your elementary mathematics, I think you know how to do that. So let me quickly share my screen. Let's list all the members of that set. I think you remember in your elementary mathematics, we did a whole lot then. Yeah. If you remember in your elementary maths in set theory, let me quickly just take us back to set theory and show us some things there. All right. In your elementary maths, we did, if you are given a set X, all right, if you are given a set, can you see my screen?
Yeah, we can see it.
All right, thank you. If you have a set X that is equal to a certain set, let me say X, Y, and Z, all right. If you have a set like this, you just pay attention. If you have a set like that, then this set, the cardinality of X, you remember in your normal, the cardinality of X is equals to 8, right? Do you know how we arrive at this? Can anybody explain? The cardinality of X is equal to 8. That means the number of subsets I can pick from this set must be 8. So let's quickly list those sets out, okay? Those sets, let's quickly list them out. So how do we know those? How do we know the cardinality? So cardinality of X numbers of elements in that set. How many elements do we have in this set? Who can tell me? What are the numbers of elements in this set? Anybody? All right.
Sorry,
I
come
have,
again. You said you were asking.
yes. How many elements do we have in this set X?
It's three now.
Yes. So that is how we got this theory. So 2 to the power of 3 is what? 8. So it's like 2
Eight. Yeah.
times 2 times 2. So that's how we got
Yeah.
this. Now let's list these sets. List the what? The subsets. So to list this subsets. So what are the subsets? So every set is the set of its own self, right? So the first set we have there, number one, the first set we have there is the set itself. So that is list the subsets. So this first set is the set itself. So that is the first set we have. All right. So the next set we have there is is X equals to the set of what? Of 2 items, right? So this is the next set we have. All right. So the next set we have in that set, all right, is the set that contain only one item. All right. So this is the next set we're going to have. The set that contain only one item. The next set we're going to have, all right, the next set we're going to have is the set that contain, who can tell me? The set that contain Y and what? Z. All right. So we have
Yeah.
Y
Yeah.
and Z. So who can tell me the next set we're going to have?
It's going to be X and Z.
Thank you very much. So the set that contains X and Z. So that is the fifth set we're going to have. What will be the sixth set we're going to have? Check very well.
Is Y.
The set that contains Y. Thank you very much. So the set that contains Y. And what will be the seventh set that we're going to have?
The set that contains Z.
Thank you very much. The set that contains Z. All right. So the set that contains Z. So that will be the seventh set. And what will be the eighth set we're going to have?
An
Yeah.
empty set.
Thank you very much. So the empty set will be the eight sets. All right. So an empty set will be the eight sets. I think you know how they denote that mathematically. So this is the number of sets I have in this set. All right. So if I'm having 4 here, you know I'm supposed to be having 16 subsets. If I'm having 4 elements in that set, I'll be having 16. All right. So let me bring down my screen and continue with the class. So in so where is my lecture notes? All right. So that is how we have this set. All right. So this budget set, now you can see that is a family set, or a family set that is subset of X. If you remember that we had a set that contained X and Y the other time, right? And we have the set that contained X, Y, Z when we were splitting our preference set. This sets when we were splitting this set the other time. So we had something like so. So we can combine all of this. So we only pick only 2 subsets there. So this family set contains 2 subsets. All right. So like this example is say one possible choice we can have is this B that contain what? Our first choice. All right. Our choice. Remember C1, we are mapping it with B. All right. It's a subset of this. So this C contain. So remember this set now, this set X comma Y is like B. Remember this B that we are highlighted here. So I said B is a subset of X. All right. B is a subset or is an element of coily B. All right. So one of that B is this guy X comma Y. Another B is X Y Z. You understand? So one choice in this part is what? Picking C dot, and where C dot represents what? Where C dot represents X, Y, which is just only this first part, all right? Which is just only this first part of my budget set. So this is my C1. So this is one choice I can pick. So I can denote it by this, or I can rewrite it by putting this entire C1 in place of C dots. I can have it that, all right? Because of space and time, so I just represent it as C dots, where my dots represent X, Y. All right. So now, if I have a choice structure that looks like this, my preference, this is my preference there. You can see my preference is what? X. So once I have picked X, I cannot pick any other thing anymore. So my preference is X. I cannot pick Y. So it means that I prefer, what this means that X is preferred to Y. From this choice that I have made here, my preference is what? X. I have picked X. I cannot pick Y because X is preferred to Y. All right. So here is another choice or another preference I can pick. I can pick my second B. All right. This is B2. I can pick my B to be my first choice. X as my first choice. I cannot pick any other preference anymore. So my preference here is what? Is X. So this is what it means. So whenever I have this choice rule, I have made this choice, then my preference is this. So choice X is I made my choice before my preference. Okay, that is what it's saying. So my preference here is what is X. All right. So another possible choice structure is C2. What is C2 dot? C2 dot is like I'm having XY, all right, and in XY I am picking X, all right. Am I from this same choice I'm picking X and Y. So I can also pick X and Y as my choice. All right. So once I pick X and Y from this choice, I cannot pick Z. So I've made a choice of picking the subset X and Y from this choice. I cannot pick Z anymore because I've made my choice. All right. So he said in this case, we see that whenever a decision maker is faced with a budget, all right, with a budget, what does that implies is that when I'm faced with a budget, it implies that we can see that if either he chooses X or he chooses Y, whenever he's given a certain budget of this. So when you use this choice structure, all right, so to model behavior, we may want to impose some certain reasonable what restriction regarding this choice. So, and that will lead us to what we call a weak axiom of our revealed preference. So, anytime, so in these choices here, we've revealed our preference here to be X, while in this second choice, we reveal our choices to be what? X, Y. So, once we've revealed a certain preference, we cannot make other choices anymore. So, but would that be the case? So we have to put some restrictions in the choice structure or in making our choice. So such restriction is known as a weak axiom or a strong axiom. So in our next class, we talk more about weak axiom of revealed preference. Once a preference is revealed, when is it weak and when is strong? All right. So with this, we've come to the end of this class. Any question? Remember, this is just a tutorial. All right. So this is what we should have done in the last class, but because of time, I was able to get to this point, and I think I have explained it to the simplest form. Ask your questions.
Can you go down a little?
Down?
It's all right. So,
Okay.
can you? So, my question is, you have, um, where was okay? Now you have where the choice rule
Where?
C1,
Yeah.
C1, which C1 is uh, X comma Y, which is equals to X. Can that be Y, and the other be Y? Can that choice be okay?
Okay. If this place here is Y.
Mm.
Yeah.
Instead of X.
Yeah. Here is
So,
Y. Yeah.
no, the up one, the first example.
Here.
Yeah.
If here
Yes.
is Y.
Why? Yeah.
Okay. And here is also Y. Fine.
Yes.
Yeah. Once I picked Y, I can never
Mm.
pick X from the set anymore.
Okay.
So Y is my preference. Okay.
Mm.
So you can pick
Okay.
Y. So
Okay.
in this case, if I've revealed Y here, do you know the choice I'm going to pick here?
It's going to be. Let me see. If you, it's going to be XZ.
Thank you very much. I'm going to pick XZ as your choice there. So because Y has been revealed, okay? So when you get to reveal axioms of preferences, we'll understand it more. So we've successfully defined what choice is, all right? So, and we've also see how to make the structures. So, and what budget set is, this budget is a subset of X, and I've splitted down this X X contain uh, 8 subsets here, and this is just one of those subset of X. So we know how to define a budget set now. We know what preference means, and we know the choice rule. I think we've we've already established a solid foundation for this course as we proceed. Thank you all. Any other question? All right. Kindly fill the attendance. I think they've passed the attendance in the chat box. So kindly fill it before you leave the class. Enjoy a wonderful weekend.